fourth chapter, that is the refraction through the plane surface, and we were dealing with the refractive index. We'll continue the topic. We were dealing with the refractive index, and we have defined refractive index in two different ways. One was through in terms of the ratio of sin I by sin r, and whereas the other way was to define in the terms of the ratio of the speed of light in vacuum to the speed of light in that medium. There were certain important points regarding the refractive index, that is or vacuum, the refractive index will be equal to 1, and in case if the two mediums are having the same refractive index, no refraction is going to take place. Another way we can say that the light passes undeviated. Now let me show you some examples to find out the refractive index of some medium with respect to the speed of light, okay, in that particular medium. The three basic medium refractive index of some medium, we will take the three medium as air, water, and glass. Now, the velocity of light, vacuum or air is considered to be as 3 into 10 to the power 8 meter per second. Whereas the velocity in glass, that is equal to 2 into 10 to the power 8 meter per second. And velocity in water. Try to remember these values, okay?
2.25.
Syllabus, you have to use these values into 10 to the power 8 meter per second. So now if I have to find out the refractive index of glass with respect to air, so we'll write down A mu G, so which will be equal to the speed of light in vacuum upon, or air upon the speed of light in glass. So it comes out to be 3 into 10 to the power 8 meter per second upon 2 into 10 to the power 8 meter per second. And finally, it comes out to be 1.5. For the normal glass, okay, we consider that the refractive index of glass is 1.5. So, in case when you are going for the experiment, we try to find out the refractive index, okay, of the glass slab. This happens to be an ideal. It should be 1.5 meter. I hope I am audible. Similarly, refractive index of water, if we try to find out, again with respect to this, so this will be your C is equal to V, velocity of light in air or vacuum upon velocity of light in water. So 3 into 10 to the power 8 upon, in water the speed is 2.25, and there's a slight difference in their speed, okay. So if you see, if you compare the mediums, you'll find that in the denser medium its velocity is decreased, okay, and this comes out to be 1.33. Similarly, refractive index of diamond, this happens to be the highest one, it is 2.41, okay, and we know that the refractive index for diamond is highest for any material, okay, and therefore we find that the since the diamond has got the highest refractive index, that is the refraction takes place a bit deeper, the light takes place to a maximum extent. Hence, we observe that the diamond is shining, okay. So the lustrous nature or the shining nature of the diamond is again owing to the highest refractive index. Now, say for example, if I want to find out the velocity of light in diamond, then we can use this formula. Okay. Say for example, so we are knowing the refractive index of diamond is 2.41. We all know that the refractive index of diamond with respect to air. This means that will be your velocity of light in air upon velocity of light in diamond. Okay, so velocity of light in diamond
Yes, sir.
is equal to c upon mu a mu d. A mu d. So c will be your 3 into 10 to the power 8 upon velocity. Its refractive index comes out to be 2.41, and once we calculate it, we find that 1.245. So if you observe, the velocity of light in case of diamond is least as compared to that of glass and other medium. Okay, this is one of the ways of using it. Now, generally, when we are saying refractive index of diamond is 2.41, we mean by saying it as it's an absolute refractive index, and that is why we are taking the formula with relation to air. Okay, uh, but it can be like the light rays may be passing from water to glass or glass to water. So, what to do in that case? Keep in mind the basic idea is that the speed of light, the refractive index of the second medium with respect to the first medium is the speed of light in the first medium upon the speed of light in the second medium. So say for example, if I want to find out the refractive index of glass with respect to water, this simply means that the, the velocity of light in water, which happens to be the first medium, upon the velocity of light or the speed of light in glass, which happens to be the second medium. Now, velocity of light in water is going to be 0.25 into 10 to the power 8, whereas velocity of light in glass is 2 into 10 to the power 8. Hence, it comes out to be 1.125. So, refractive index of glass with respect to water. Now, keep in mind, here refractive index is changing because when you are using, because when you are using the relation, or when you are allowing the light to pass from the glass, from water to glass, okay, it is the refractive index of glass is not going to be your 1.5. Okay, and why it is not going to be 1.5, I hope this calculation is made it clear. Similarly, if you try to calculate for refractive index of uh, water with respect to glass, now in that case you will find that this will be equal to 1 upon refractive index of glass with respect to water, that is 1 upon 1.125, it comes out to be 0.89. Now this also suggests us, say for example, if the light is traveling from water to glass, suppose water and here we have glass, so light is going to bend more, refractive index is more. Suppose here we have got glass and water, so this is going to bend less. Okay, it's not going to be straight, it's going to be bending a bit away from the, so which means that its refractive index will be less. So I hope this is clear. We can also find using the relationship of the refractive index. Okay, like I have to find out the refractive index of glass with respect to water, and I know the refractive index of glass and refractive index of water. So what I can do is it can be refractive index of glass by refractive index of water. Now, how we are going to get this? In a simple term, if we try to calculate refractive index of what glass with respect to water, this happens to be the velocity of light traveling in water upon velocity of light traveling in glass. Now, for example, if I consider the case, okay, medium 1 to medium 2. Now, velocity of light traveling in water, it means that Vg upon C by Vw. Okay, using the basic formula of the refractive index. And once you solve this, you'll get Vw by V. Now, C by Vg will give us the refractive index of glass, and C by Vw will give us the refractive index of water. So in other terms, we can say that if the refractive index of the second medium with respect to first medium, we can write down as the refractive index of the second medium upon refractive index of the first medium. So this is the relationship which you can use in case if you are not using the absolute refractive index. Okay, so if you know the refractive index of the two medium and the light is traveling between those two mediums, out of which one medium is not your air or vacuum, then you can directly find out the refractive index using this. I hope this is clear to all of you. Write down in your chats. Words, you can say that the wavelength is inversely related to the refractive index, which means that if the which means that if the refractive index is more, okay, the wavelength is going to decrease. If the refractive index is less, the wavelength is going to increase. Okay, that means if the light is traveling from a denser medium to the rarer medium, okay, we find that the refractive index will be less than 1, and in that case the wavelength is going to increase. Whereas if it is traveling from the rarer medium to the denser medium, the refractive index is going to be greater than 1 and its wavelength is going to decrease. Okay, the first case, denser to rarer, wavelength is going to increase. The rarer to denser, the wavelength is going to be less than the original wavelength. Okay, so now this leads us to the next topic, that is the factors affecting the refractive index of the medium. So up till here, I hope it's clear to all of you. Why Pratham is out? Why they all are out? Why they are late? So many students. I hope it will be clear to you. What we are doing, we are allowing the light to travel. We are allowing the light to travel from one medium to the another medium. Let the one medium be air and the other medium be any medium M. Okay. In air, the wavelength of the light is lambda and velocity of light is c. In the other medium, the wavelength is changed to lambda dash and velocity changes to v. The frequency in both the medium remains same. Okay, so now we know that V is equal to F lambda. This is the standard formula we have studied. So F will be equal to V by lambda. So this formula only we are trying to apply. Here it will become your F is equal to C by lambda, and here it will become F is equal to V by lambda dash. Now we know that the frequency in both the cases are going to be same. Okay, and as a result we can equate C by lambda is equal to V by lambda dash. Okay, or we can change this formula for lambda dash, that is equal to V by C into lambda. We all know that mu is equal to C by lambda, C by V. Okay, this is the standard formula which we have already studied. Okay, velocity of light in air or vacuum upon the velocity of light in the medium, and therefore we get, we can write this as lambda dash is equal to lambda by mu. Okay, so this gives us the relationship between the lambda dash and mu. So now we move to the next topic, that is the factors affecting the factors affecting refractive index, okay, of a medium. Now, factors affecting the refractive index of the medium. The factors affecting the refractive index, there are three factors which are affecting the refractive index of the medium. Okay, uh, they are the nature of the medium, the physical conditions such as the temperature, and color or wavelength. Now keep in mind, this is very important, and it's important to understand the relationship, okay, because the further portion when you are studying and when you study with the different different wavelengths means different colors of, especially for the visible light. Okay, so how they are going to behave while they are passing through the various medium other than the air or vacuum. So first of all, we deal with the nature of the medium. Now, when we say nature of the medium, okay, now in a simple term, we can define the nature of the medium by the property that is called as its optical density. That is, a medium can be rarer medium and medium can be denser medium. Again, keep in mind, it is a relative thing depending upon what are the two mediums through which the light is traveling. Okay, so now once you consider the optical density, that is whether it is your rarer medium or it is your denser medium. Okay, what implication does this have? This is basically changing the, has the implication or has the effect in terms of the change in the velocity, change in the speed of light in that medium. So the speed of light may be increased or speed of the light may be decreased. Okay, so now how the speed of the light is going to be related to the refractive index? Keep in mind, the speed of light in air or vacuum is constant. Okay, now we all have studied just now that mu is equal to C by V, that is speed of light in air. Now, if I consider that C is a constant, okay, then mu is inversely proportional to V. That is, if the speed of light increases, then the refractive index is going to be less, means the bending of the light will be less. If the speed of the light decreases, then the bending of light is going to be more. Okay, in other words, we can say that lesser, if you are allowing the light to travel from uh, rarer medium to the denser medium, where the speed of light is decreasing. So in that case, the refractive index is going to increase. That is, refractive index of the second medium is going to be more. Whereas if you are allowing the light to travel from the uh, denser medium to the rarer medium, so in rarer medium the speed of the light is going to increase and the refractive index is going to be decreasing. Okay, so depending upon how the light is traveling, your refractive index of the medium may be less or more. So therefore, if you allow the light to travel from air to glass, okay, we find that the speed of the light is going to be decreased and refractive index will be more. So for air, the refractive index is 1. For glass, the refractive index is 1.5. So you find that it is increasing. Similarly, if you allow the light to travel from air to water, okay, again with respect to the water has 1.33. But if you compare glass and water, you find that the glass is denser. Okay, so its refractive index is more, and water has got a lesser refractive index, which is equal to 1.33. So I hope this is clear, this point. We are here, what we are considering is the velocity of the light and the optical density. Okay, so that is what we are basically considering it. So now we move to the next topic, that is next factor, that is the physical conditions such as temperature. So the second factor happens to be physical condition such as temperature. Okay. Now we all know that as the temperature increases, the velocity is going to be increased, and as the velocity increases, the refractive index is going to decrease, which means that increase in temperature decreases the refractive index. And as a result, we can make out that refractive index is inversely proportional to the temperature. So you can say that if a light is traveling from a cooler to a warmer region, okay, the refractive index of the light is going to decrease, whereas from warmer to cooler, the refractive index is going to increase. The third factor which we are considering, that is the color or wavelength of the light. Now, we all know that light consists of 7 different colors, okay, but the speed of these colors in air, the speed for the different color is same, and therefore the effect what we see in case of your air or vacuum, we find that it is a white light. Okay, you all know the concept of that. Okay, the effect is your white light. But if you allow these colors to pass through say a prism, okay, you see that you are able to see the band of the 7 different colors. Now why this band is appearing? This is appearing because we find that while passing through the glass, the speed of different color is altered. Okay, or the speed of different color is different. Okay. Now, if you consider the speed for the red color, okay, this is going to be greater than the speed for the violet color, because the refractive index for the red color is going to be less than the refractive index of violet color, and this is arrived because the wavelength of the red color is more than the wavelength of the violet color. So see, you all are interrelated. Okay, we all know that the wavelength of red color is around about 708,000 7,800 angstrom, approximately 800 angstrom. Somewhere it is written, somewhere in nanometers, it will be 780 or 800 nanometers. And the wavelength of violet color is your round about 4,000 angstrom, okay, or 400 nanometer. Clear? So what we find, wavelength is more, refractive index is less. Wavelength is less, refractive index is more. Okay, so we can make out that the refractive index is inversely proportional to the wavelength of the light. Keep in mind, this is applicable when it is traveling in any other medium other than air. Okay, say for example, glass or diamond or water. Okay, so you find even in case of water also, if you see with a certain particular angle, okay, you will be able to see the different colors, although in the normal case it is not visible. Okay, so these are the three factors which are affecting the refractive index of the medium. uh, Yesterday I was not able to give you the notes. Today I will be giving you the yesterday's notes also and today's notes also, so don't worry about that. So I hope up till here it is clear to all of you. Okay. Others are not joining. There are only 180 to 176 students only. Please inform them. Otherwise, they will be in big problem. And later on, they will create a problem to them only. All right. Now we come to the next topic, that is principle of reversibility. Principle of principle of reversibility. That means if the light is traveling from medium 1 to medium 2, is the light can travel in the same way or behave in the same way while traveling from medium 2 to medium 1. Now, according to the principle of reversibility, it says that the path of the light can be reversed. Path of light is reversible. Now, what does that mean? Say, for example, if I have a medium 1 and I am having a medium 2, and I allow the light to travel from medium 1 to medium 2, okay, normal should always be dotted line, arrows should always be marked. In all the experiments, in all the diagrams of the this, arrow should be marked. Let S and S dash be the junction of the two mediums. Okay, so this becomes your angle I, this becomes your angle R. All right. Now this is the normal. Now, if I allow the light to travel along the same path from medium 2 to medium 1, it is going to follow the same path, provided, what is the difference? The difference is in terms of, for medium 1, it becomes your sin I upon sin R, that is mu 1 mu 2. That is the refractive index of second medium with respect to first, while the light is traveling from the first medium to the second medium. Now, for the when the light is traveling from second medium to the first medium, your angle I will be equal to angle R, which is given over here, and angle R will be equal to angle I, which is here. So here it becomes your sine I. So here the refractive index of the first medium with respect to the second, because the light is traveling from the second to the first, this will become sine R upon sine I. This is not your, but because the Snell's law is angle of incidence upon angle, sine of angle of incidence upon sine of angle of refraction. So while the light is traveling from the second medium to the first medium, okay, so the angle I is the same as what we had in angle R earlier, and angle R is same as what we used to have the as angle I for the previous case, and that is why this is okay. So now what we have, for refractive index of second medium with respect to the first, sine I upon sine R mu 2 1. This is sine R upon sine I. So which means that if I find the product, that is mu 1 2 into mu 2 1, this is equal to sine I upon sine R, sine R upon sine I. As a result, mu 1 2 is equal into mu 2 1 equal to 1, or mu 1 2 can be written as 1 upon mu 2 1, or vice versa. That is mu 2 can be written as 1 mu 1 upon 1 mu 2. Okay, so this is about your this. Now what is the implication of this, or what is the application of this? It simply means that if we have the refractive index of glass with respect to air as, let's say, 3 by 2, that is 1.5, okay, I can find out okay. So this is what we can use it. Okay, so principle of reversibility means that it is going to follow the same path if you reverse the path, provided you are allowing the light to be incident at the same angle at which it was getting refracted. Okay, so I hope this is clear to all of you. Okay, yes, Parth, Ayush, Sakshi, Kritin, basically so according to the principle of reversibility, it says that the path is going to be reverse. That's all. Okay, and therefore you can say that the refractive index of the second medium with respect to the first medium is reciprocal of the refractive index of the first medium with respect to second medium. That is what is the significance of this. Okay. Now we come to the experimental verification. Okay, of what we have studied, that is laws of refraction. This experiment you are required to do it in the lab also. There are various aspects in this. The main aim of this experiment, okay, is to verify the Snell's law. Not only this, we can also use it for the various other purpose, okay, like verifying the Snell's law, finding out the refractive index of the medium, finding out the lateral displacement, and verifying the principle of reversibility. All these four can be clubbed together in this experiment. So maybe in your examination, or maybe in your practicals, it might be one of the aims may be asked. So what we can do in this experiment is that to verify Snell's law. Okay, that is sin I by sin r all of is equal to constant. Constant. The second purpose of this experiment is to find refractive index of glass, mu g or mu glass. Third purpose is to find out the lateral displacement. And the fourth purpose is to verify the principle of reversibility. Okay, so these four objectives we can achieve using this experiment. This is a very simple experiment. It's called as your we are using the material which we use is your uh, rectangular block of glass. Okay, glass slab, what we call it as, and just a sheet of paper, pens, protractor for finding out the angle, and pencil for drawing. Okay, that is your experimental part. So I simply try to explain you using a diagram. So what we do, we keep the rectangular piece of glass block. Okay, I'm drawing and mark its boundary. Let it be P, Q, R, and S. Now, the rectangular block of glass piece, we have got two refracting surface. So we can consider any of one of the refracting surface. And in case of verifying the principle of reversibility, we can use the other because we will be using both the refractive. So we first consider any point O, say on the surface as R, and then draw a normal. Let this point be O. Then using the normal, we draw a straight line making a certain angle. This we consider it as angle I. Okay, let the normal be N and M. Okay, then we place two pins over here, P1, P2. Okay, and looking through the other side of the glass slab, that is looking from the PQ surface of the glass slab, we try to place two more pins such that all the four pins appear to be in the same straight line. Okay, uh, just like you have done it in case of law of reflection. So you were placing two pins and then seeing through the image. Okay, in case of reflection, the reflected rays we were considering. So image we were seeing through the on the mirror, and then we were trying to place it on this. Clear? So now I'm drawing the final thing. Okay, this let N1 and M1 be the normal on the surface PQ. Here we have placed pin P3 and P4, uh, and then we have, so let the name be A, O, B, and C. Okay, this will be representing A, O, N will be representing angle I, M, O, B will be representing angle R, and M1, B, C will be representing your angle of emergence. So this is your incident ray, refracted ray, and your emerg- emergent ray. Okay. Now here what we do, we draw a table where we have serial number, we have angle I, we have angle R, we'll find out sine I, we'll find out sine R, and then we'll find out the ratio sine I by sine R. Clear? These are the columns which we make for the different values of angle of incidence, say 40 degree, 50 degree, 60, 70, and so on. Okay, maximum of 5 readings we take. Okay, so for different diagrams we will be drawing with a different angle. Clear? Now what we do, for the corresponding value of angle I, we'll write down the value of angle R. We'll find out the sine value of each of these angle I and sine value of each of these angle R. Okay, and then we'll find out the ratio of them. That means the value of sine. Now sine table you will be using to find out the sine value. Okay, I hope you have studied in your trigonometry how to find out the sine, cosine, and tangent value using the table. So here you will be finding out the ratio, and here you will be getting the values. Now the first part, how we can say what should be here. Okay, here the value is going to be same, and as the value remains same, therefore we can say that the first law is obeyed, or rather the first objective is achieved, that is the verification of Snell's law, that is sin I by sin R is constant. And practically it may be slightly varying, but theoretically it should be same. It depends upon the nature or the quality of the glass slab. Next is to find out the refractive index. So you get a constant value. This is nothing but your This is nothing but your refractive index. This is going to give you the refractive index. That this value is also going to give you the refractive index of the glass. That is two part is being done. Now the third part, that is lateral displacement. So for lateral displacement, what you do, from the incident ray, you use your ruler and draw a straight line. Now, this is basically the path the light should have been traveling if we have not kept the glass slab. Okay, but due to the refraction through the glass slab, the light has deviated from this path and has taken the another path. So this difference or sideways displacement of the path is called as your lateral displacement. So this value, lateral displacement, will be represented by x. So if you are able to find out this value, that will give you the lateral displacement. That is the third aim has been achieved. And finally, to verify the principle of reversibility. To verify the principle of reversibility, what we are going to do is we are going to find out the value of E and value of I. All right. And angle I should be equal to angle E. If you find that angle I is equal to angle E, principle of reversibility has been followed. So I hope this is clear to all of you.